Euler's method for estimating the solution of an initial value problem. So the learning goals for this video include being able to carry out 2 to 3 steps of Euler's method by hand, and also to be able to determine when Euler's method over or underestimates the actual solution to the IVP. So how do we estimate the solution to an IVP? First, let's look at a particular example. So let's say we have this example, y prime is equal to 5 minus 2y. That's the differential equation, and the initial condition that we want to start with for this example is y of 0 equals 0. And the problem here, the question is asking us to estimate y of t, the solution to this problem, at 0, 0.5, and 1. Now because this is a linear differential equation, we've already seen how to solve these analytically, meaning we can get a formula for the function y of t. But instead, we're going to use the fact that we know how to solve it to perhaps check our solution later. And instead, we're going to focus on coming up with an approximate to this function. So how do we do that? Well, the first thing we want to do is let's just draw a sketch of what we're going to build. And so here is the graph of the function, or at least its approximation. I'm going to draw y of t, or let's just call this the y-axis. And now we know that the function definitely starts at the origin. And so what we want to do is we want to get all the way out to 1, and we'd love to calculate all the values in between, but that'll take a lot of work. And so instead, we're just going to calculate the values at a few points. In particular, 0, which we know already, 0.5, and 1. So in the absence of a solution that fills in all the points in between, what could we possibly do? Well, you'll notice that we have an equation that tells us the slope of the curve at any y value. And the y value initially here is 0. So when I plug in y equals 0 here, it tells me that the slope at that value should be 5 minus 2 times 0, which is just 5. So that means the slope here should be 5. So I can fill in a little line segment there representing the slope. Now I could see that if my slope is positive, I'll start with y values going up. And once y is bigger than 0, the slope should now decrease. But I don't know how quickly the slope decreases, and I don't want to calculate it at every moment in between all the way up to 0.5. So what I'm going to do is I'm going to cheat, and I'm going to pretend that 5 is a perfectly good slope all the way out to 0.5. And I'm going to go out to this point and calculate what is the value right there. Well, we know if the slope is 5 and the run here is 0.5, the rise must be 2.5. So this should be 2.5. And what do we do once we get out to 2.5? Now, finally, even though we should have changed the slope all the way along here because the formula tells us that the slope will decrease as y increases, I've waited till this point, and now I'm finally going to update my slope. So I can plug in a new value of slope 2.5, sorry, a new value of y in here is of 2.5. And what does that give me? That gives me y prime is equal to 5 minus 2 times 2.5. 2 times 2.5 is 5, so that's actually equal to 0. And so if I have a slope of 0 at this point, that tells me for my next interval, I'm going to just have a flat line like that. And that will be my next approximation as well. Now we know the function does not do this, but this is our Euler's method approximation. So how do we calculate this from formulas instead of just drawing a picture? First, let's define y0 to be the y value at t equals 0, which in this case was exactly 0. Now I want to choose a y1, and this y1 will be, well, as we've constructed it here, it'll be the y0 value starting at the same point, or at the y value that we were at last time. And then we want to have a specific slope. So we're going to say plus 5 was the slope we figured, times how far are we moving across? Well, it's 0.5. And so this gave us 0 plus 2.5, and that's 2.5. So that gave us our first estimate. Let's put this into a slightly more general notation. Let's say we're going to call 0.5 our delta t. We call this a time step. So our time step delta t in this particular example was 0.5. And so if I now rewrite it in terms of the time step, and let's also rewrite, instead of writing 5, let's write the general formula for the slope. So let's just do that right here. So y1, where did I get these numbers? y0 was just the initial condition, plus the slope here was whatever is on this side of the equation for y prime. So in this case, it was 5 minus 2y, and what did I plug in? I plugged in y0. And that gets multiplied by how far we're going to the right, delta t. So this is the formula that I would use to get this value of y1. How do I get y2? Should calculate it similarly. Take y1, the height of this one, and add to it 5 minus 2 times y1, because this is the slope we expect at 0.5. We're going to multiply that by delta t. So that's the slope multiplied by the horizontal increment, and that gives us a vertical increase. So we can continue doing this, and we can get a whole sequence of points. Now in this case, by the time we get here, we're already at t equal 1, so we're done. But if we had more, or let's say our delta t was smaller, we might need to do more and more of these. So the general formula would be yn would be yn is equal to yn minus 1 plus 5 minus 2yn minus 1 times delta t. And that's the general formula for updating Euler's method. So this quantity here is specific to this problem. But let's say in general we had an equation y prime equals some more complicated function of y. Then we would have yn is equal to yn minus 1 plus, and now in place of this slope, which was 5 minus 2y, we are going to put f evaluated at yn minus 1 multiplied by delta t. So that is the general update formula. And we can use this formula. In this case, we've only demoed it with delta t equal 0.5, but we could also have chosen delta t equal 0.25, and then we would get 4 intervals between 0 and 1, or we can take it smaller and smaller. In fact, as we take delta 0 smaller and smaller, the approximation that we get from these straight line segments gets better and better. And the reason for that is if you rewrite this as yn minus 1, and then that's by bringing this over to this side, divide by delta t, you could see that the left-hand side of this is approximately the derivative, and the right-hand side is f evaluated at the y value, which is a discrete version of y prime. This is before you took the limit as delta t or h went to 0. So if I take delta t smaller and smaller, it becomes more and more like y prime. So there's one more thing that we need to talk about, and that is how do you figure out whether this straight line version, approximating the solution, over or underestimates the actual solution. So in this case, we know that the actual solution is an exponential curve like this. And you can get that directly by finding the solution by techniques discussed last week in class. And so notice what we're doing when we build this solution. We say right here at the origin, we're going to take the tangent line to the actual solution as the slope for a lot longer. What happens in the meantime? This keeps a constant slope, but the estimate or the actual solution slope decreases as we go. Why does the slope decrease? Well, that's because its second derivative is negative, and so it's concave down. So anytime a solution has a region that's concave down, we would expect a tangent line to be above the curve. And so the tangent line we're using to estimate the value of the function will overestimate. Similarly, if the actual solution were concave up, and we were estimating it by taking tangent lines in pieces, then we would underestimate the solution. And that is our introduction to Euler's method for solving differential equations.